Hello, this recording is to help you with 3.03 logarithmic functions and their graphs. During the lesson today, we're going to talk about inverses of exponential functions, so relating it to what we've seen back in Unit 1 when we were looking at our exponential functions there. We're going to, of course, look at the common logarithms, which have base 10, your natural logarithms, which have base e, and the graphs of the logarithmic functions that we are going to be creating. All right, first things first, I want to take us all the way back to the first unit where we talked about our exponential functions a little bit. And don't forget, an exponential function is one that increases without bound here or decreases without bound. We can go ahead and see that that does, in fact, pass the horizontal line test, which means that it has an inverse that is a function. The inverse of an exponential function is a logarithmic function. So you can see the exponential function here reflected over that line y equals x to create your logarithmic function right here. Notice that your base of your exponential function is going to be the base of your logarithmic function. So that means that we can actually convert between the two forms. So to go from logarithmic form to exponential form or vice versa, we can go ahead and use these equations here. So the base raised to the exponent here equals your x. So I always start with the base, and then the exponent is going to be what it equals, and then your x here is going to be what it equals over in your exponential form. So write this down in your notes, and we'll go ahead and look at converting between the two forms here in our next example. All right, so we have some logarithmic functions here. Let's go ahead and change them to exponential form. So again, I always start with the base. So our base is 2 to the third power will equal 8. And we know that that is true. In part B, our base is 3, so it's 3 to the 1/2 power. And remember those fractional exponents, they can be changed to your square roots there, or your radical equations, I should say. So that is actually going to be the square root of 3, which we have right here. In part C, it's going to be 5 to the -2 power, and remember that is the same thing as saying 1 over 5 squared, which is 1 over 25, which is what we have here. For part D, we have 4 to the 0 power, and we know anything to the 0 power is equal to 1. And lastly, we have 7 to the first power is going to equal 7. Which is what we have right here. We do have some basic properties of logarithms. In fact, we already saw some of them being used up above. Anything to the 0 power is obviously going to equal 1. We saw that with example D. If your base and the number right next to it are the same, you will always have that equaling 1. We saw this with example E, right? So notice how it was 7 to the 7. And that is going to equal 1 there. If you have log base b of b to the y power, again, that log base b of b is going to cancel out, and it will just equal that y value. Again, because if you were to change this to exponential form, you would get that by equals by. And the last property here is if you have b raised to the log base b of x, again, those bases and the log of b is going to cancel each other out, and you are left with just the x value. Make sure these 4 properties get written down in your notes because you're going to see them a lot throughout the unit. All right, let's go ahead and evaluate some logarithmic and exponential expressions. So right now they're all given in the logarithmic form. We're going to go ahead and solve that. If we can use a property, we'll most definitely do that. So here in part A, I'm going to go write that as exponential. So 2 to some unknown power equals 8. Well, we know that 2 cubed equals 8. However, if I didn't know that, I could try to rewrite 8 right off the bat. I can rewrite 8 as 2 cubed, right? And then I have that property that log base 2 of 2 cancels out, and I'm left with just that 3 for my answer. So a couple ways we can look at part A. I'm going to go ahead and rewrite part B here. I'm going to rewrite that as log base 3 of 3 to the 1/2 power, because that's how the square root can be written, as a rational exponent. And because I have log base 3 of 3, those cancel out, and I'm left with just x equaling 1/2. And then in part C, notice you have your bases the same, so 6 to the log base 6 of 11. So these are going to cancel out, and you're left with 11 for your answer. All right, on the very front slide, remember I mentioned one of the standards that we were going to be looking at today was the common logarithms. So we've been looking at logarithms that have different bases. So above we had base 2, base 3, base 6, but the common logarithm is written with base 10. All right, so if you don't see any base written there, we know that that's going to be base 10. So in this first one, I have log of 1 equals 0 because 10 to the 0 power is equal to 1. And then we have all of the other properties that we can follow here as well. So again, just keep in mind that my base is 10 if it's not written, because that's what the common logarithm base is. All right, so let's go ahead and evaluate these here. So again, these are all common logarithms. They all have base 10 because I don't see a base written here after my log, right? So I know that these are base 10. So this first one, I'm going to go ahead and rewrite to see if I can get 100 written in base 10. And we know that that is 10 squared. So of course, this is just going to equal 2. In part B, we can go ahead and rewrite that radical expression as a rational exponent by doing 10 to the 1/5 power. Again, those are going to cancel out, and we're left with 1/5. In part C, I'm going to go ahead and write that as 10 to the -3 power because I have a fraction there. So that will equal -3 once I use my properties. And because I had 10 to the log of 10 of 6, that 10 log 10 cancels out, and we are left with just 6 for part D. In example 5 below, let's actually solve for x. So I'm going to change this to exponential form. 10 to the 3rd power equals x, because remember I start with my base, then I figure out my exponent, and that's going to equal x. Well, that 10 cubed is 1,000 for the first one. And then changing my logarithmic form to exponential form, we use base 2 to the 5th power equals x. Therefore, x is going to equal 32. All right, so we've dealt with logarithms. Now let's talk about the natural logs. Logarithms that have base e are what we now call natural logarithms. We often use the abbreviation ln instead of log. So when you're looking at your calculator, you'll see that log button, and then right below it, you're going to see your natural log button. Okay. So if I have something written as log base e of x, we know that that is just referring to the natural log of x. So if you see natural log without a base, we know that the base is going to be e. It has all the same properties that natural logarithms do, or logarithms do, sorry. So you can see here, anything to the 0 power is still going to be 1. E to the first power is going to be e. And then because you have a base that are the same, those cancel out. And again, because the bases are the same, they cancel out. So you can see they have the exact same properties that your common logarithms do. So let's go ahead and look at the examples with the logarithms now. So I'm just going to write it with that common base e. You don't have to. But I am going to change the square root of e as e to the 1/2 power. So you notice that those cancel, and I am left with just 1/2. In part B, the natural log of e is going to cancel out, and we're left with 5. And e to the natural log is going to cancel out in part C, and we're left with just 4. All right, let's talk about the graphs of your natural log functions here. The graph of the natural log function looks like the one that you see up in the upper left-hand corner, and here are all the characteristics for it. Transforming your logarithmic graphs or your natural log graphs are the exact same as we would transform any other graph. So for example, in part A here, notice how you have a +2 and it's inside your parentheses. That means you're shifting to the left 2. And if you want to go ahead and actually graph these just to validate it, feel free to do that. But in A, you're shifting it to the left 2 spaces because you have a +2 there. In part B, I would actually probably rewrite this, and we can rewrite that as taking a negative sign out, and that allows you to reverse that subtraction inside the parentheses. Therefore, in part B, because there's a negative, we do reflect over the y-axis. And because I have a -3 inside my parentheses, you're still shifting it right 3 spaces. For part C, notice out front we are multiplying by that factor of 3. Therefore, there is a vertical stretch by a factor of 3. And then in part D, you have adding 1 at the end. So if you're adding 1 on the outside there, that is shifting up 1 unit. So all those transformations that we've learned before still hold true with our natural log graphs and our logarithmic graphs. All right, let's go ahead and evaluate the logarithm without using a calculator. So for the first one, I'm going to change it to exponential form. So to do that, I get 6 to what power equals 1. Well, the only way I can get anything to equal to 1 is to have that exponent equal 0. In the next one, 3 to what power equals 81. That's going to be 3 to the 4th power. You could also go ahead and rewrite that so they have the same base. So how can I rewrite 81 so it has a base of 3? That would be 3 to the 4th power. And we notice that property would cancel out there, and we're left with the 4. In fact, I'm going to go ahead and rewrite number 3 here as 1,000 to the negative 1/2 exponent there, which technically I want to rewrite 1,000 so it has base 10. Well, that's just 10 cubed. I can go ahead, I have a power to a power, so if we multiply those exponents, we get a negative 3/2, and now my properties come into play, so I know for a fact that x is going to be negative 3/2. The fourth one here, natural log and e cancel each other out, so we're left with just -4. And again, natural log of 1 is just like we saw up in the very first example. That's going to be 0 because you're going to have e to what power equals 1. Well, the only way you can get it to equal 1 is when that value is going to be 0. All right, you may want to pause it here and try these on your own and then check your answers. Evaluate without using a calculator, so using your properties. This first one, we're going to get 3. Second one is going to be 0.5. Third one is 6. Fourth one is 8. 14. And 1/5. The last thing we're going to see here today is transforming our graph. So what is happening? Notice how we have the natural log of x plus 3 inside parentheses. So we know that that is shifting left 3 units in that first one. And because I have a -1 outside, so -1 plus log of x, we know we're shifting down 1 unit in this next graph. All right, hopefully you have those properties written down. They're definitely going to be very useful for you throughout the unit, and they're pretty easy to understand once you are familiar with them. All right, that's all I have for 3.03, so have a great day.